So, as a continuation from the last video, we talked about the structure on the right being a major resonance contributor because it has all of its octets satisfied, whereas the structure on the left, the carbon, only has 6 electrons, so the octet is not satisfied. But rule number 3, or the third consideration we want to look for to figure out which structure is major, says that the positive charge is on the least electronegative atom. Well, carbon is to the left of nitrogen on the periodic table, and so it's going to be less electronegative. So on the left structure, we actually satisfy this rule, but on the right structure, we do not, because we have the positive charge on a more electronegative atom, which is nitrogen. And so that, again, is not necessarily the major consideration to figure out which structure is the major of the two. And so the structure on the right is major because octets being met is more important than the positive charge on the least En atom, and then also it is more important than the negative charge being on the most electronegative atom. Right, and so again, the right structure is major because all of the octets are satisfied. Now let's continue on with another example. So our next example, I'll just go ahead and draw just the two oxygens or just the two atoms involved in our resonance, and I'll go ahead and color code these lone pairs. And so when we have the resonance structures, let's number this actually 2 and this 1. The lone pairs drop to form a bond. This is a positive charge, excuse me. Lone pairs drop down to form a bond between 1 and 2, and therefore we have this resonance structure. Now we said two things happen at the same time in resonance. What happens is that you end up having your positive charge move. Where did it go? It went, I'll go ahead and put, oops. I don't know what this is. Okay. So we had a positive charge there, and then it moved to the oxygen. Now let me get back to our black and finish filling out the lone pair. And so these are our resonance structures. We have to ask ourselves which one's major and which one's minor based off of the rules. And so we look to the left and we count the number of electrons on carbon. So we got 2, 4, 6. That carbon is not happy. It's not at an octet. The oxygen, however, is. It's got 2, 4, 6, and the lone pair is in the blue for 8. So this oxygen is happy, but the carbon is not on the left structure. When we go to the right structure, we have 2, 4, 6, 8 is the bond in the blue, and so we have a octet on that oxygen. Now if we count the carbon, we have 2, 4, 6, and then 8 being the blue bond, and so we have full octets there. So that would make this the major resonance contributor, even though on the left structure you have the positive charge on the least electronegative atom. So again, octets trump having the positive charge on the least electronegative atom. So now if we give a try at the resonance hybrid, let's go ahead and follow our rules to draw a resonance hybrid. We said let's look at what is conserved in both structures. So I'll go ahead and actually erase this positive charge, and I'll put it in black. And I'll look now only for what is conserved both structures. So these carbon groups essentially are in both structures. This bond, even though it's a double bond on the right, at least this green bond is in both. This bond is also in both. these lone pairs at the bottom are also in both. Now I'm going to change the color of this positive charge because it is not in both, and I want to use green to indicate that it is representing what's the backbone of the molecule. So let me go ahead and draw now in green the backbone of my molecule. So I'll start with my carbon groups, and then I'll go ahead and put the oxygen. Again, we know there's at least one green bond in both. The blue on the right is not present in the left, so we're just going to do the lone pairs also are present in both. These green are present in both structures, but the blue lone pairs are not. And then lastly, this bond is present in both structures. So that's my backbone. Now let's take a look at what has changed. On the right-hand side, I have a blue positive charge. So it's right on the oxygen on the right structure, but on the left structure, it is on the carbon. And so on the right-hand side, I have that blue bond between the carbon and oxygen. I do not have that on the left-hand side. So in order to portray that, I would do a dashed line. So this would be my resonance hybrid. Right now, we have to figure out which, so we said that the major contributor is essentially the right-hand side. And so this positive charge with the bond is probably going to contribute more to the overall structure, creating a larger partial positive on the right side than on the side. Why? Because the left side is a smaller, minor contributor of resonance. Now, let's do one more example. Put a negative charge adjacent on this carbon, and we're going to go ahead and drop these down, kick these up. Let me go ahead and draw the lone pairs on there. And so our resonance structure will look like this. I'll go ahead and notate this bond in red. And now I'll show that they jumped up on the oxygen. Excuse me, screen is moving. And so we have a double bond there, which I'll portray in blue. So these were the lone pairs. They drop down to form, oops, that bond, right? And now we're, again, two actions. The bond went up, and then we have now a negative charge there on the oxygen, right? If we look, 1, 2, 3, 1, 2, 3. So the lone pair went and became a double bond. That was the first step. The double bond between carbon and oxygen became the red lone pair in the right structure. Which one is major? Which one is minor? Well, we have a negative charge on the most electronegative atom on the right structure. Right, and so let's take a look. Does everything have an octet? Yes, it does. So if I actually were to draw in the implied hydrogens there, I could show that this structure has 2, 4, 6, and then the blue lone pair. So that carbon has 8 electrons. Check. This carbon has 2, 4, 6, and then the 8th would be in the red double bond. So that carbon's good. And then if I count 2, 4, 6, and then the bond that's red would make 8 electrons around that oxygen. So that's good. So everything in the left structure has its octets met. On the right-hand side, if we take a look at and draw the implied hydrogens, what do we have? 2, 4, 6, and then 8 being in the blue bond. Then this carbon would have 2, 4, 6, and then 8 being in the blue bond. So that one's good. And then 2, 4, 6, and then the 8th being in the red lone pair. So both of these structures have an octet. So we have to essentially go down our list. Both structures have octets.
and the negative charge on the most electronegative atom. So this would put that there. The negative charge is on oxygen, which oxygen is more electronegative than carbon. So we're happy with the right structure as the major resonance contributor.